Our next speaker is Dr. Pam Heinselman. She is a research scientist with the National Severe Storms Laboratory, and she has 20 years experience in the areas of weather radar, severe storms, and warning and forecast applications. She is a former employee of SIMS who transitioned into NOAA. And in 2016, she moved from the Radar Research Development Division to the Forecast Research Development Division to serve as the Warn-On Forecast Program Manager. And now this summer, she became the Division Chief of the division. So she is also a winner of the Presidential Early Career Award for Science and Engineering, and she's going to talk a lot about the radar meteorology work that is going on in SIMS. Thank you very much, and that has gone on as well.
Thank you. It's my pleasure to be up here, and I wanted to kind of set the tone for what do I mean when I say radar meteorology. And so I have a basic definition up here. So radar allows us to observe the atmosphere, right? So we're talking about the environment as well as storms, and then using that information to make predictions, whether that's in a nowcast sense or also with models. And what you see here is essentially a radar history of the development that has happened within Norman, starting with the NSSL Doppler, followed by the Cimarron dual polarization radar. So that was the first one developed by mostly NOAA folks, I believe, at that time. And then that was followed by the KOUN radar, which became the kind of the prototype for the upgrade for the National Weather Service. And during that time, also, we started developing Doppler on wheels types of systems, because with the systems we had developed before, of course, it depends on the storms coming to you. And sometimes you want to take yourself to the storm. And so we see a number of instruments there, some of them done in collaboration with the university, I think all of them done in collaboration with the University of Oklahoma. And the beauty of being able to take them to different places is that we can observe phenomena that may not be as frequent here, such as that windstorm that you see there, and the storm that was sampled, storms that were sampled in Colorado. You see the mountains and perhaps some snow in the background. And I understand that work done there has recently resulted in the production of a new radar site in Colorado. So what an exciting outcome from that. And then going to the Blue Dome, when that was painted blue, it's a phased array radar dome. We got a lot of feedback from Norman, the city of Norman. Didn't necessarily like that, but it's withstood its time, and started with a SPY 1A system that was there and that I worked on with several other folks for several years, and has recently been replaced with the Advanced Technology Demonstrator, which Sebastian will be talking about. Some people like to see if they can barf or not on an airplane, and that would be people who get on the P3. And that would not be me. My stomach couldn't take it. But that is another important, we have radar instruments on that, on the front and in the back, that collect very important observations. Terry Schur is one of the SIMS folks out there who has spent time on that. And then, of course, we have clamps, which is related more to looking at the environment itself. Okay. So I thought we would start with a little bit of fun, okay? I had not put together a word cloud before, so I wanted to learn how to do that. And what I did was I took all of the papers that SIMS authors on them that were on the NSSL website that had to do with mobile radar. Okay, and so that's where this word cloud comes from. And so mobile is really big, but I thought it was interesting. We also see lightning is showing up here quite a bit. We've got dual, and that dual goes with Doppler. It's not dual pole yet, but that dual goes with Doppler. And I think it shows that there are a variety of storm types and integrated work that goes on in the field. It's not only about the weather radar. This is what you get if you take every single article that has the word radar in it that also has a SIMS author within it. And so now we see some other themes that are starting to show up. We see polarimetric in big letters. We actually see row HV shows up. I thought that was kind of cool. ZDR, and we also see Zernich. Okay, so lots of interesting names there. I would say the number of articles, like it was so long, it took me forever to get all that text and put it into this. So there's been a really high number of papers that are related to radar with SIMS authorship. So Jeff just talked about the history, right? One of the things that's a challenge is that, you talk about the folks who were here early, like Steve Koch. If you go back and you try to find a paper that says SIMS in the authorship during that time, it's impossible, right? They're not out there. I think one of the first ones I found actually had Eric Rasmussen on it. But there were a lot of postdocs and students and things like that were supported early on. And in the research that I did, what I found was that the installation of the 88D network was really a kickoff for SIMS development, the SIMS scientists that have grown over all this time. And of course, that happened in the late 80s to the early 90s, and that was around the time that I started my career. And what was great about that is instead of having just a few radars here and here, now we have this national network from which we can draw data at a number of different phenomena in different geographic regions and things like that. And the National Severe Storms Laboratory received a gold medal for that, and I bring that up just because it's a good thing, okay? So that is really the kickoff, and like I said, one of the first people I found as an author was Eric Rasmussen. And you'll see on the diagram in the middle there, he has all these radars that are WSR 88Ds. And the paper I'm referring to there was written in 1994. And within Vortex, of course, they were bringing in other radar instruments, those trendy cars with instruments on top, or geek mobiles. Some of you may have gotten to go in a geek mobile with what's his name? Bill Paxton, right? So he actually came out and was on one of those chases with us. But all these different radars that have evolved over time have allowed us to go out in the field, make observations, learn more about severe storm processes. And so this is a sampling of different titles from papers that have used weather radar in that capacity, and we see a really nice diverse set of topics, again, from lightning to bow echoes, of course, supercells and tornadoes, as well as work along the dry line. And this is just a small sampling of what those look like. Okay. So the next person that I found, who's a key person who's been around for a while in the mid-90s, was Alexander Ryshkov. Okay. And why do I bring up him? Because he came on board at the time when the Cimarron radar was being developed, and he was brought on to, I see him as really kind of the start of deep learning and investigation of what we can do with dual polarization radar. And he did use that system to do the work that's shown here. A lot of the early work was focused on how might the data from a dual polarization radar help precipitation estimates. And so the diagram that you're seeing here, the bottom line message is that if you use KDP in your radar rainfall estimates, instead of only Z, you end up with more accurate rainfall estimates. And the reason for that is the ability to not gain information not only about the size, but kind of a medium bulk volume size, but then also the distribution or the number of drops therein. It ended up being the precipitation estimation, being able to do that better, was really the reason why polarimetric radar ended up being sold. Okay, so that's what brought about the transition of polarimetric radar to operations. And this is just a diagram showing the performance of the polarimetric algorithm versus a conventional algorithm with radar estimates from a special network that was in Oklahoma. Okay, but there's more, okay? So we not only got better rainfall estimates, but we got hydrometeor detection. And it's not only hydrometeor detection here, I'm showing in the middle, of course, perhaps the more sexy part is being able to identify hail, rainfall intensity. Of course, we've gone from that to tornado debris signatures, as well as ZDR columns and all other kinds of fun signatures that are interesting not only from a process perspective, but from an application perspective. And I'm sure that Don will be talking about that in his presentation. And of course, it's not only about severe weather, it's about winter weather and being able to see transitions and bright bands and going from rain to snow and things like that. And then, of course, there is our improved data quality. And that's from the ability to identify things such as biological scatterers, so insects versus birds, and also AP, for example. So we can have cleaner data. And why does that matter? It matters not only for the meteorologist and for finding the signal that you want, but also for the use of the data in numerical models. Okay. So this collaborative work between folks at SIMS and NSSL resulted in yet another gold medal. Okay, and this was in 2014 for developing and implementing dual polarization technology that then was an upgrade that occurred across the United States. This would not have happened without the cooperation between NSSL and SIMS. I would say it was critical to that. Okay. So now we're going to move on to talking some about phased array radar. And this is a picture of the group that worked on the development of that system and got it up and running and then started working with the data. And we see Doug Forsyth there in the middle, who was the leader of our group, the Research Development Division, and he always liked to put R2D2 on the slide, RRDD. You get it? Okay. So I put that on there in homage of his leadership. But again, here we're looking at a group of both NSSL and SIMS researchers working together. Okay. Two of the major questions that from a science perspective, that radar meteorology perspective that we looked at were twofold. First, how does the rapid adaptively scanned radar data improve the understanding of severe weather processes? So I'll show some examples of that work, as well as then how can this information, if number one is true, be used to produce more accurate and timely warnings? Okay. So here's a subset of papers, and if you know some of the people on this list, you'll see we've got postdocs, we've got some students on that list, and I just wanted to bring that out just to bring forth the point of the importance of SIMS in bringing students, postdocs, and folks like that, kind of rejuvenating, and building the workforce. I think that's really important. So you see a whole slew of papers here, and I don't want to talk about any of those in detail, but this talk would not be the same without a radar animation. So on the top, what you're looking at is 26-second observations through a hailstorm versus 5-minute observations. And these are actually both from the phased array radar SPY 1A antenna. So this is a totally fair comparison, I guess, kind of. But anyway, you can see a lot more of the detail, and that's what we were looking at, from a process study perspective. Are you seeing information that is being missed? And I think in this case, that's fairly clear. We see much better the development of the hail core. We know it's significant due to the 3-body scatter spike, etc. So that's just one example. Here's another set of papers that gets more on the application side in working with students with forecasters in the test bed and seeing then what does the usability of that look like? Can we improve warning performance? Can we improve the decision process? And that's what these papers looked at. And here, let's see if I can get it to play. So I had to show not only a vertical cross-section, but I had to show a PPI, so we can have equal time, both for hail and rotation signatures. So here we're looking at circulations actually this was just before Erin. How many people were here during Tropical Storm Erin? Okay, there was some hands in the room. So we had these low-top supercells that occurred prior to that, and these are some data that we collected during those storms, and this is also one of the cases that we used with forecasters in the test bed to look at the utility of the data. So what did we learn from all this kind of in a nutshell? Well, we learned that the data we were using, which was mostly 1-minute updates, provided more detailed information about storm processes that advanced scientific understanding, check, and also improved what we learn about improving forecasters' capabilities using the data, situational awareness, ability to make mastery decisions, performance in terms of severe and tornado warning lead times by several minutes, also improvement to POD reduction in FAR. So we had some really good findings there. And finally, I couldn't end this presentation without talking about how radar matters for war-on forecast. And this is one example of that, where we're looking at the probabilistic QPF with radar data and no radar data. And this is work by Nusrat Youssef. And we can see the black contour is the stage 4. And we can see a big difference in terms of where the probabilities and the high probabilities lie with respect to the stage 4 with the radar data and without the radar data, as well as the improvement in the fractional scale score. So radar data matters. Okay, so I was also asked to talk a bit about what's next. And of course, the next big system that we have available is the Advanced Technology Demonstrator. And Sebastian, I'm sure, will be telling you more about that. But based on my experience, one thing that's for sure is late night data collection. Right? So that's where we kind of get to play like a forecaster and be up late at night and put in a lot of hours collecting important data sets. And then, of course, there's the science component. And my intuition tells me there will be a lot of focus on the microphysics and microphysical processes. Now we have more rapid updates with the dual polarization data, and so a focus on those. How do they relate to storm dynamics, thermodynamics, and specific hazards? And then finally, hopefully with any new system, it's great to have a surprise discovery. So perhaps something that we don't even have on our minds right now will be found, as well as, of course, the development of QC, so we can do observational and numerical modeling studies. Forward operators for dual polarization parameters, that's really starting to kick off now, and it would be great to be able to use some of the data from this radar in that capacity, as well as visualization, and probably, you might want to think about a new acronym instead of PRECE. Okay, so that was the acronym that was used for all the experiments we did with forecasters, and I will leave that up to the new group to decide what they want to call that experiment. Thank you.